Now, what is a good way for me to determine the intermolecular force for a particular molecule? Should I think about ID-ID first? Or should I think about PD-PD first? Or should I think about hydrogen bond first? My suggestion is we follow this guideline. I think the easiest intermolecular force to determine is hydrogen bond because it is very obvious. Does it have HF bond? Does it have HO bond? Does it have HN bond? If it has any of these bonds present, then yes, you'll be able to form hydrogen bond. Straight away, we can determine the intermolecular forces without taking into consideration the shape of the molecule. The objective is to try to minimize drawing shapes of molecules because it is troublesome, time-consuming. If it is not required, then we don't want to do, correct? So first thing, which I think is easiest, is we see what does it have HF bond, HO bond, HN bond. If yes, we know that it can form hydrogen bond. If not, then we consider, okay, are there any polar bonds present in the molecule? Is there an electronegative element, fluorine, oxygen, nitrogen, halogens, or sulfur? If yes, most likely we will have a polar bond. If not, then this molecule will be non-polar. So examples will be like my hydrocarbon. Hydrocarbon is just any permutation of carbon and hydrogen. Carbon-carbon bond is non-polar, whether it is a single bond, double bond, triple bond. Your carbon-hydrogen bond is also considered as non-polar, so the entire molecule is non-polar. Dominant attraction will be ID-ID attraction. Of course, elements, if it is element bonded to itself, there's no difference in electronegativity, so this guy will also be non-polar. So overall, the dominant intermolecular interaction will be ID-ID attraction. So you notice, if there are no polar bonds present, the entire molecule will be non-polar. There's no need for me to consider the shape of that molecule. You don't draw the shape of the molecule, and then we determine what is the shape. Then you realize that, hey, there are no polar bonds in the first place. Then there's no dipole moment for us to cancel anyway. So it becomes an unnecessary step. So therefore, I think it is a good idea to try to follow this. The objective is to try to minimize or to delay drawing dot cross diagram and to delay considering the shapes of molecules, because in itself, this is a bit tedious. So we try to avoid it as much as possible. So if there are no polar bonds present in the molecule, we don't need to bother about the shape of the molecule. That guy will be non-polar. It will have ID-ID attraction. Next, if I have polar bonds, then I will need to consider the shape of the molecule. Then I consider the dipole moment. This is important because the dipole moment is like a vector. There's a direction, there's a magnitude. So the dipole moment only comes in when we look at the shape of the molecule and we visualize where the bonds are actually pointing. Only then we look at the dipole moment. Some of us will accidentally just jump in and, let's say, for example, this consideration here, we just jump in and we just make use of the structure that is given in the question. So if I give you SO2 in this way, some of us will just make use of this and we happily draw the dipole moment, wow, this bond, there's a dipole here, there's a dipole here, so just nice, they will cancel each other, so this is non-polar. But you haven't taken into consideration the actual shape with respect to sulfur. You notice sulfur actually has a lone pair that you have to consider, and the shape with respect to SO2 is not linear, it is bent. So the dipole will be pointing in different directions, and therefore the dipole moment will change, right? And we will have to consider whether it cancels out or don't cancel out by taking into consideration the actual shape. So this one is important because some of us will just make use of whatever structure that is given. We just straight away draw the dipole without considering the actual shape. So this is a big error that we will have to keep in mind. The examples that we have are all here. You notice the dipole moment doesn't cancel out. HCl is pretty straightforward because there's only one bond, which is polar. So there's only one arrow, nothing to cancel this out. Obviously, this will be polar. SO2, earlier what we have mentioned is please consider the lone pair. Make sure you take into consideration the actual shape first, then you go and draw dipole. Otherwise, again, we will make mistakes. We will have the wrong shape and we will have a wrong conclusion in terms of the net dipole moment, whether it cancels or don't cancel. But if I know that this guy is bent, and you notice this SO bond is like generally pointing down, this SO bond is also generally pointing down, so I would be able to visualize that, okay, there's a net dipole moment which is like pointing in this direction, pointing down, and then nothing to cancel this guy which is pointing down. So net dipole moment is not equal to 0, and therefore this bond will be polar. And just to clarify, because some students will start to say that, hey, I have this lone pair, this lone pair isn't this negatively charged? So wouldn't this guy have like a dipole moment which is pointing up because it is negatively charged? Actually, this misconception is quite common. Some students will say that lone pair is negative, there's a dipole pointing up. It's not true, because we have to understand what is a dipole moment in the first place. So let's go back to the definition involving a dipole moment, and we have to understand this well, all right, so that we do not have this misconception. So where does the dipole moment come from? First thing is, I need to have a covalent bond. I need to have a bond pair. And this X and Y, there must be a difference in electronegativity. So one guy is more electronegative than the other guy. The one which is more electronegative is a delta minus. The one which is less electronegative, it is a delta plus. And because of that, there's a dipole moment from the delta plus guy to the delta minus guy. So this is my dipole moment. Dipole moment is only for bond pair, only for polar bonds. So if I come back to my lone pair, you notice it's not possible for the lone pair to have dipole moment because this is not even bonded to something else. It is not even a covalent bond. It is not a bond pair. Lone pair cannot have dipole moment. Only bond pairs have dipole moment if there is a difference in electronegativity. So please keep this in mind. Don't anyhow go and draw the dipole moment for lone pair because you think that lone pair is negative, so therefore there's something pointing up. So that's not how we interpret dipole moment. Dipole moment is because of a difference in electronegativity in a covalent bond inside this bond pair. Alright? So for NCl3, nitrogen is more electronegative than Cl. So you notice that all these arrows pointing up. So we should expect a net dipole moment pointing up. And again, nothing to cancel this upward arrow. This is polar. And CHCl3, CH bond is non-polar, so there's no dipole moment pointing up. So we have this CCl bond pointing down, one dipole for CCl bond pointing down, again another one pointing down. So we have a net arrow downwards, nothing to cancel this out. So most likely this guy will also be polar. So this is what we mean. Dipole moment don't cancel. Overall, this will be polar. You notice what we can only do is we can have a rough estimate whether it cancels out or not. We cannot actually calculate or prove what is the magnitude of this dipole moment. It's very difficult for us to do because all these are three-dimensional. This is 3D, this is tetrahedral, this is trigonal pyramidal. It's actually very difficult for me to actually draw out and calculate the net dipole moment. We can't do that. On paper, it cannot be done because it is three-dimensional. For planar species like HCl, which is flat, SO2, which is flat, because V-shape of bands is flat, or planar species, if they are flat, yes, we can still, on paper, we can work out the net dipole moment. It's just basically the vector sum, right? But for three-dimensional species, you notice we have no way to determine the net dipole moment. Which actually brings us to this next point. What if the dipole moment cancels out exactly? If it cancels out exactly, then we say that, okay, the molecule will be non-polar. But it's actually, in theory, very easy to say that, oh no, if the dipole moment just nice cancel out each other, then overall this is non-polar. But it is so difficult for me to prove that the net dipole moment is equal to 0. Because there are certain shapes that are three-dimensional, it's very difficult for me to show that. So my suggestion is we memorize which shapes have high symmetry, because we are already familiar with shapes of molecules. We memorize which shapes have high symmetry, and we just remember that if it have high symmetry, then the dipole moment will tend to cancel out, and therefore it is a non-polar species. So which shapes will have high symmetry? It's actually fairly easy. All our basic shapes have high symmetry. X bond pair, no lone pair. That means linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. They're all basic shapes, and so therefore they will be highly symmetrical, and the dipole moment will naturally cancel out each other exactly. That guy will be non-polar. There's another shape which is not a basic shape, but it is highly symmetrical. That will be my square planar. For bond pair to lone pair, that guy is also highly symmetrical. My suggestion is we keep this idea in mind. If you have a basic shape, or if you are square planar, and the surrounding atom has to be the same, then the dipole moment will cancel out, and it will be non-polar. Because eventually we will do this by memorizing. So what do I mean by that? Because if, let's say, I ask you, okay, can you prove to me that carbon dioxide is non-polar? The net dipole moment cancel. Can we prove that? Yes, because this is linear. So I can always draw a dipole moment pointing in one direction, another dipole moment pointing in an opposite direction, and equal in length. I can show that it cancels out. Net dipole moment equals to 0. So therefore, this is non-polar. Alright? Now for BF3, because this is trigonal planar, if it is flat, I can still draw on paper, but I need a protractor, draw the vector sum, draw these 3 arrows, same length, and I can show that this arrow plus this arrow plus this arrow will go back to the same spot. Vector sum equals to 0, so therefore this net dipole moment is equals to 0. For planar species, no problem, we can do that. But how about CCl4? If I ask you, can you prove to me that this CCl4, the net dipole moment will cancel exactly, it goes back to 0? It cannot be done. I don't think any tutor will try to prove it to you because it cannot be done on paper. Because this is 3-dimensional, what we're trying to do is we're trying to use paper, which is 2D, to try to prove this guy, the dipole moment cancels out, is actually not possible. So usually what we will do is we will just say that, oh no, this CCl bond, there's like a dipole pointing down, there's something pointing down, there's something pointing down. So these 3 guys are pointing down, then there's this net dipole pointing down here, which will be just nice cancelled by this guy. So probably they'll tell you something like that. So net dipole moment equals to 0, so this is non-polar. So you notice, it's just that your tutor tells you that these 2 somehow will cancel out, so you just remember this is non-polar. So I don't think it's particularly useful for us to try to imagine or try to calculate, see whether this can be done. So it's a lot easier for us just to remember the outcome. You just say that, okay, this has high symmetry, and then the dipole will just cancel. I think it'll be a lot easier for us to do that. Okay? So same goes for the other shapes. The idea that we want to talk about, or the idea that we want to have the appreciation is, because for 3D species, when you have many bonds, it's not so easy for me to visualize the dipole moment. So I think it is a lot easier for me to just say that, okay, I know which one has high symmetry, so therefore the dipole moment will cancel out. I just remember basic shape, non-polar, provided that the surrounding atoms are the same. Let's say for example CCl4, surrounding atoms will all be chlorine, then this is highly symmetrical. Because earlier we have an example involving basic shape tetrahedral configuration, but I have 3 chlorine but 1 hydrogen. So if I have 3 chlorine and 1 hydrogen, then this is no longer symmetrical. This guy will be polar. Okay? So we just need to remember basic shape, square planar, highly symmetrical, it will be non-polar. Then for other shapes like band or seesaw or T-shape or trigonal pyramidal, square pyramidal, they tend to be polar.